All right, hey guys, this is Lab 4 on oscillation. So in this video we're going to see, we got the contents. So we're going to go to the introduction and theories used, the logic used through equations, experiment data and analysis, computational model, results, and then the what does it mean for this week. So introduction and theories used. So the purpose is to be able to predict the motion of the spring and the mass system by using the energy principle and Newton's second law. So those principles, Newton's second law, we know F net equals ma, which we can use that force and equate it to what we know the spring force that's happening plus the gravitational force that's going to give us what we need to know to be able to calculate the energy. Once we calculate the energy, we can then see that because the change in energy is going to be consistent through the entire experiment, that it's going to either be kinetic energy or spring energy that's being changed, or gravitational energy, given that the height is dropping. All right, so we see that, unfortunately, my video is not playing. It having a download error because I am currently in Texas, but we're gonna do what we can. So we're gonna look at our X position and our Y position. Currently they put over time. The time doesn't really matter because we're using energy here, but it's just easy to graph it out that way. We're gonna see we have an oscillation right here. That oscillation is where we're going to see the potential of spring energy and the kinetic energy then transferring. So whenever it is completely stretched out, that's going to be where, therefore, like at the trough and the peaks of these oscillations, we're going to see that the potential spring is going to be at its highest, kinetics at its lowest. In that midpoint, we're going to see the kinetics the highest. That's going to go the same for the Y as well. We can just calculate those oscillations with the peak and trough of those waves. Our givens are that it's at rest. It started at the origin. That's really just relative. I said at the origin in my experiment. We know G. We know the mass is 0.402 kilograms. K is 6.3, and then the L naught is 0.123 meters. Right. So computational model. So here we just had to go through the variables that are within the spring formula. So we had to go through US, meaning potential spring, potential gravity, and kinetic. Those are the three energies being used in this energy principle, given that the change in energy is going to be constant, right? So once we get those lined up, we're looking at these 8 lines right here, the ones that we had to change. We set them equal to their equations, right? So we have K, it's 0.5, times the mass, times the velocity squared, and that goes for all these, and this is updating, right? So we're going to look K minus Ki, right? So we're going to look at the initial and then subtract the initial from where it's at currently in order to be able to graph it. So we do the same similar things for all of them. We just plug in the equation, and we plug in its current minus its initial so we can graph it. So besides that, that's basically did very similar things to the other variables, just so we can graph them and update them throughout the computation. All right, so we look at the results. The experiment matched very closely to the model. Only difference is maybe some things we didn't take into consideration, like wind. I don't know, anything that was like, there's thousands of factors that you get, or not maybe thousands, but just factors that you don't really compute in a computational model, but it does match very closely. So what we're seeing with the big graph right here with many lines, so we're seeing that the change in spring energy and the change in gravitational energy is matching with the changing kinetic energy, right? So we see that when spring energy is changing and it's at 0, right, that's when its kinetic energy is going to be the highest. That's when it's at its peak or trough, because it is going to be all transferred into kinetic energy. And the same goes for the gravitational energy. See, when it peaks in gravitational energy, generally the kinetic energy is furthest from 0. So let's go on. What does it mean? So is the energy principle satisfied? Yes, they all go between those 3 energies: kinetic, spring, and gravitational, right? And that makes it go in an oscillation where it follows that wave pattern that we saw on the previous slide. You can see in this graph that they just change into each other, right? All right, so make 2 oscillation periods. We look at this graph that we had on the other slide. We're going to see that it goes between like 0.11 and then negative 0.11 in the x direction. And the same in the y. It goes from down 0.07 meters, right? I mean, that one is set at 0.7, so you'd have to add minus 0.07 or plus 0.07, right? But that is the oscillation. Thank you for your time.